Here is a classic problem that involves particle motion. In calculus, we love talking about particles zipping around left and right on a number line, or sometimes up and down on a number line. And we look at its position, its velocity, which of course is its speed with direction, and its acceleration, which is its change in velocity. All right, so here we go. Let's just go through and do this problem together. An object located 5 meters to the right of the origin, and remember, origin in this context always means 0 on the number line, okay? An object located 5 meters to the right of the origin at time 2 seconds travels along a number line. The velocity function of the object is known to be v of t equals t cubed minus 3t squared. Find and state the position function. Okay, well, we know the velocity. To find the position, we're going to find the antiderivative of the velocity function. So let's do that. Antiderivative, also known as the indefinite integral of a velocity with respect to time. So I'm just going to, let's see, what has a derivative of t cubed? It's going to be t to the 4th, and then of course I need to multiply by 1/4 because I don't have a coefficient. What has a derivative of 3t squared? Oh, t cubed, sure. The thing that's nice about antiderivatives is you can just take the derivative and see if you did it right. The derivative of t cubed is 3t squared. The derivative of 1/4 t to the 4th is 1t to the 3rd. Perfect. And of course, we always need a plus c there because there could be a constant in my position function that disappears when I take the velocity, when I take the derivative, right? When I take the derivative of position function, there's a constant that might disappear. Velocity just tells me my speed and my direction. It doesn't tell me at all where I am in space. All right, can we find what that c is? Let's see. Were we given information? I think we were, right here. An object located 5 meters to the right of the origin at time t seconds. That's saying, let's let x of t equal my position, right? So if I'm saying x of t is my position, this is telling me that at 2 seconds, my position is 5. And it's a positive 5 because I'm to the right of the origin. All right, that's enough for me here to find my c. So, and let's be even more clear here, right? Let's say x of t equals the integral of v of t. All right, so now let's use this information. We're going to say that 5 equals this position when my time is 2, and I think we can just do the arithmetic there. Let's see, that's going to be 1/4 of 16, that's 4, minus 8 plus c equals 5. All right, that's going to be c equals 9, I believe, okay? All right, so I'm going to write out my position function so it's all in one place. My position function is 1/4 t to the 4th minus t to the 3rd plus 9. There's my position function. I have finished part A. Let's move on to part B. During what time intervals is the object slowing down? All right, an object is going to slow down when velocity and acceleration are working against each other. So if my velocity is positive and my acceleration is negative, that's like a weight pulling against my velocity. I'm going to be slowing down. If I'm moving to the left, in other words, with a negative velocity, and my acceleration is positive, I'm going to, again, be pulling against my velocity. So a particle slows down when the velocity and the acceleration have opposite signs. Conversely, a particle speeds up when velocity and acceleration are working together, either both positive or both negative. All right, so to do this, we have to really figure out when velocity is 0, because then I can figure out when it's positive and negative. I need to find when acceleration is 0 again, so I can find when it changes sign if it does. We're looking for critical points, basically. So here we go. Let's dive into velocity. So I'm going to set velocity equal to 0 just so I can analyze it. All right, I'm going to factor out a GCF of t squared. Okay, so my velocity is going to be 0 at times 0 and 3. I'm going to make a nice little number line here. I'm going to label it. So 0, 3. And now I want to figure out, well, what's happening in between those times? So let's plug in maybe 1. Let's see, 1 squared times 1 minus 3. Well, 1 squared is positive, 1 minus 3 is negative. So in this region, my velocity is negative, which means my particle is moving to the left. Let's plug in a number bigger than 3. Let's say 4. When I plug 4 into my velocity, I'm getting something positive. So at time 3, not only did the particle stop, but it changed direction. My particle is moving left from 0 to 3 seconds, and then now my particle is moving right. Let's look at the acceleration. Oh, wait, do I know what my acceleration is? I don't know what my acceleration is, but I can find it. Acceleration is the change in my velocity over time. It's the derivative of velocity. So acceleration is the derivative of my velocity. So I'm just going to take the derivative of this. That's going to be 3t squared minus 6t. Okay, let's find when acceleration is 0 for the same reasons. I'm going to factor out a greatest common factor of 3t. Okay, so it looks to me as though acceleration is going to be 0 at time 0 and time 2. Look at what I'm going to do. I'm going to make a nice acceleration number line right underneath my velocity. I'm going to line everything up here. So my acceleration is 0 here and 0 here. Let's plug in some values in between to see what's happening with my acceleration. When I plug in a 1 into my acceleration, this positive times the negative, negative acceleration here. When I plug in, I don't know, like a 4 or a 3, I'm going to get something positive. So I have a change in my acceleration. Okay, so I'm looking to see when the velocity and the acceleration have opposite signs. That's when my particle will be slowing down. Let's see, that looks to be right here. Look at that. From 2 to 3, my velocity is negative, my acceleration is positive, so my particle or my object, whatever it is we're calling it, slows down on the interval 2 to 3, since velocity and acceleration have opposite signs. Remember, this is the non-inclusive interval notation from 2 to 3. You could use, and if you didn't like writing it like that, you could say 2 is less than t, which is less than 3, but I think that's easier. Okay. All right, let's move on to C. C asks for the displacement. Well, displacement, of course, is the definite integral. It's the definite integral from 0 to 5 of your velocity, right? Of course, if we wanted to, we could graph this velocity function and find the signed area, the area between the curve and the x-axis, and find the displacement that way. But we can find it this way. So what's the antiderivative of velocity? Of course, position. It's the end position minus the beginning position. That's the definition of displacement. It's also fundamental theorem of calculus part 1, the definition of a definite integral. There's your displacement. Now, we don't have to do the antiderivative because we already have it. It's right here in my position function. So it's just going to be 1/4 times 5 to the 4th minus 5 cubed plus 9 minus 1/4 0 to the 4th minus 0 to the 3rd plus 9. You can throw that into a calculator or even leave it unsimplified. When I put it into a calculator, I got 31.25, which means I ended 31.25 meters to the right of where I began. Okie dokie. On to D. Part D. We're looking for the total distance that this particle traveled on the interval 0 to 5 seconds. All right, so we already know from our velocity that my particle traveled to the left for the first 3 seconds, and then it turned around and started traveling to the right from 3 to 5 seconds, okay? So there are two ways to do this. One way is to figure out how far did I travel to the left? How far did I travel to the right? And add those up. Now the thing that's sneaky about that is we would just have to make sure that all my distances are positive. What makes everything positive? Absolute value. So one method is to, since we know when I turned around, I'm just going to find my change in my position over the first 3 seconds. So that's going to be x of 3 minus x of 0. And notice I just put that in absolute value, so I get a positive distance for that. And then I want to figure out how far I traveled to the right. And that was from 3 seconds to 5 seconds. And of course it doesn't matter since I have the absolute values here. I could have done x of 0 minus x of 3, or x of 3 minus x of 5. It matters not. This is one way I could find the total distance I traveled. And I think my answer ended up being 44.750. And in AP Calculus, we always like leaving 3 decimals. We want it to be accurate to the nearest thousandths place. Okay? Now that's one method, or if you have a calculator handy, we can do something super cool with absolute value. We know, of course, that the definite integral from 0 to 5 is going to give me this signed area between the curve and the x-axis. By signed, of course, area by definition is positive. So if I call it signed area, I have positive area, that's the area above the x-axis, and negative area is the area below the x-axis. So I know that if I took the integral from 0 to 5 of my velocity, that would give me my displacement, right? That would take my positive area and my negative area and add them together, my change in position. We already talked about that. But if I want to make all of the area positive, I could just slap a absolute value around v of t. That will reflect any area that's below the x-axis over the x-axis, so everything will be in positive land. And if you put this in your calculator with that absolute value, you'll see you get the same answer. Shall we see how that works? Let's do it. Let's look at our calculator. Just for fun, let's look at this graph. I'm graphing the velocity function. I chose a window from 0 to 6, just so we can see. So here, of course, my velocity is in negative land. Then my velocity is 0 at 3 seconds. Then the velocity is in positive land. So my particle's moving to the left and then to the right. To find the displacement, that's the definite integral. Let's do that here for fun. That's second trace choice 7. My lower limit of integration is 0. My upper limit is 5. I'm finding the displacement from 0 to 5. Woo! There's the negative area and the positive area. That's kind of fun. And there's our displacement, 31.25. We ended 31.25 units to the right of where we began. Let's see what happens when I put an absolute value around this velocity function. I'm just going to go to my catalog. Second 0 is one place to get your absolute value. Again, I'm going to type in my velocity function. All right, so now my velocity function is all in an absolute value. And as predicted, look, sure, it reflected all of that area that was in negative land to positive land. So now when I take my definite integral from 0 to 5, it's going to give me all positive area, which would give me my total distance. Isn't that kind of cool? 44.7498, which we rounded to 44.750. On to part E. E asks, is the object moving towards or away from the origin at 4 seconds? Well, let's think about what information we need to answer that. We need to know what direction I'm moving in. That would be velocity. Positive velocity, I'm moving to the right. Negative velocity, I'm moving to the left. Origin, remember, is the 0 on the number line. So what other piece of info do we need? Yeah, we need to know where we are at 4 seconds. If I'm to the right of the origin and moving to the right, I'm moving away. If I'm to the right of the origin but moving to the left, I'm moving towards the origin. If instead I'm starting to the left of the origin and moving right, oh, I'm moving away again. I'm moving towards again. But if I'm starting to the left, if at 4 seconds I'm to the left of the origin and my velocity is negative, I'm moving away. So you see, you have to look at the position and the velocity at 4 seconds. So let's do that. I just need the values of x of 4 and v of 4. Right? You can just plug them into your functions, or you can remember your velocity number line. I'm pretty sure we were moving to the right at that point. But we can also just go ahead and sub in 4 into my velocity. And I think you can very quickly see, oh, that's going to be some positive value. And we can sub in 4 into our position function. Let's go ahead and look at that. You can certainly use your calculator or the calculator in your brain. I think we can just use our brains here. This is 1/4 4 to the 4th. Isn't that the same as 4 to the 3rd? 4 to the 3rd minus 4 to the 3rd plus 9. I think that's just 9. Yeah? And 9 is positive. So I'm starting at 9 to the right of the origin, and my velocity is positive, so I'm moving right. So I'm moving away from the origin. And my evidence would simply be, since x of 4 and v of 4 have the same sign, if the signs of the position and the velocity were different from each other, we'd be moving towards. I hope that was helpful. Have fun.